Okay, so hi everybody. My name is Dennis Tay. So I'm going to be teaching the second half of this Lie theory course. And so as Erlen mentioned at the beginning, the first half was quite analytic in nature and introducing Lie groups and transition to Lie algebras. So this second half is going to be more algebraic. Yeah, towards the end, it will be quite combinatorial in flavor, actually. So a lot of really interesting stuff that I want to tell you about. But yeah, so as I understand, you guys were starting on representation theory, but since we've had a little bit of a break, so I thought it'd be good to just review some definitions, give you guys a lot of examples, and just explain some motivations about where we're heading, I guess, with this course. Okay, so I've already put on the screen some definitions. So let's just run through some of them, and then I'll start giving some examples and explaining. Yeah. Okay, so we're going to let V be a finite dimensional vector space, either over R or C. Although when we study representations, it's easier to take V to be complex. Okay, so we're going to focus on those cases. Okay, so a G representation is a homomorphism from a Lie group into the invertible linear transformations on the vector space. Okay. So I'll also use this commonly used notation G dot V. Okay. This is so instead of writing all this pi all the time. Okay, so pi of G is an invertible linear transformation. It acts on V. Okay, but this is a bit of a mouthful, so I'm going to shorten it to G dot V. Right? A G representation is an action. It's a way of specifying how G acts on a vector space. Okay. We define corresponding infinitesimal, the corresponding Lie algebra to G, so this frac G, and can define a corresponding G representation, a frac G representation. Okay, so little pi acting on this V, it's an infinitesimal action of the group. Okay, there it's a homomorphism from this Lie algebra to the Lie algebra of big GLV. Okay, and so you guys have seen before that this just means the linear transformations on V, not necessarily invertible. Okay. And I'll also use this this dot at the infinitesimal level for the Lie algebra. So X dot V is this guy. Okay. Please ask questions. Just if anything's unclear, okay, just so that I understand where you guys are at. Okay. A couple more definitions, and then we'll get to some examples. So a non-trivial subspace. Okay, so sitting inside V, but not zero and not the whole thing. So a non-trivial subspace W. We say that it's G invariant if G acting on W, it preserves W. You stay in W. And similarly for the Lie algebra. Okay, and then we'll get later on into so-called building blocks of representations, so-called irreducible representations. And namely, if you don't have any of these non-trivial G invariant subspaces, then we say that the representation is irreducible. Okay. So why do you want to study representations as maybe a good starting point? Okay, so even though we've been specifying up to this point, restricting to matrix Lie groups, I mean, here in this definition, okay, you don't have to talk about a matrix Lie group. This could be a general Lie group. And basically, a homomorphism is a map that describes this as a bunch of matrices, okay, once I fix a basis on V. Okay, so it's a concrete way of thinking about how G can be represented, but moreover, it's how it's acting on a vector space. Okay. Right, and actions really are pervasive in mathematics, group actions. The simplest example is, the Euclidean group of rotations and translations acting on the plane. Right? And if I pick, this acts transitively, in the sense that from any point, I could get to any other point in the plane. It has a stabilizer at any point. So if I pick an origin, the orthogonal transformations about that point fix that point. Okay, so group actions really come up all over the place. So this is a representation specifies an action on a vector space. So on the one hand, you can think of this as like an abstract thing on this side, on the input side. Like G may not be represented as a bunch of matrices to start out with. It may just be a vector space with a bunch of abstract bracket relations. Okay, and what this homomorphism does is it associates to each one of the elements over here some matrix, some linear transformation. Okay, so it's a concrete way of thinking about this object or this object. Okay, but moreover, whenever you have an action on a space, there are important questions associated with this. For example, on this space V, which is being acted upon, you could ask, are there any invariant objects like tensors that are fixed by every element in the Lie algebra or every element in the group? Okay, that's an important question. It leads to nice objects, distinguished objects. For example, the discriminant of cubic polynomial or quartic polynomial or higher degree polynomials, you could view it as a certain invariant tensor. Okay, so we'll get to some of those exercises and examples later on. But in studying representations, you get to understand some more about the structure of the Lie algebra itself, particularly when you study the so-called adjoint representation, which I'll review shortly. Okay, so we'll study the structure of these Lie algebras, in particular so-called semi-simple Lie algebras, which in some sense are kind of opposite to the solvable Lie algebras that you guys have talked about before. And we'll see a lot of really rich structure. And it's really this second part of the course is linear algebra phrased in an extremely beautiful way. It's a beautiful piece of mathematics. And as I mentioned, towards the end of the course, we're going to be getting to some more combinatorial things. So, I mean, what this course ultimately will have to do with pretty things like this, okay, root systems, okay, or things like this, that's coming up. Okay. So so if I don't get to it before the Tromso gathering, I'll certainly show this to you in Tromso. Okay. Any questions before I get going? Okay. So examples. Okay, so for a matrix Lie group G, we have, of course, a few basic representations associated to it. Okay, so we have the so-called standard representation. Okay, so here G is it's a matrix Lie group. It sits inside GLM. So you have an inclusion into GLM C. Okay, you can do it over R as well if it's a real Lie group. Okay, so this is GL of CN. And then similarly, frac G is also a matrix Lie algebra already, so you have an inclusion into GL C. Okay. So endomorphisms on CN. Very important, however, is the so-called adjoint representation. Okay, so here we're going to call this map, instead of capital Pi, it has this name big ad. Okay, so this is a homomorphism from G into invertible linear transformations on frac G. Okay. How is it defined? So given any capital A sitting inside big G, then I have to tell you a transformation that takes as input something from frac G and then gives you an output also in frac G. Okay. So it's the transformation that takes as input some X, okay, in G. This is in G. And then I'm just going to conjugate it. Okay, so this result also is in frac G. Okay, but because A is invertible, right, this map is, so this linear transformation here is invertible. Okay, so we're sitting in capital G. When I take the corresponding Lie algebra representation, so that's this little ad map. Okay, so this is a representation of G, okay, on G itself. Okay, so I'm gonna, for an input in, okay, so let's call I'll use little a, okay, it's inside here. Okay, so given any little a, I tell you linear transformation on fraction. Okay, so here, take as input an x. And what I'm going to do, I'm going to bracket with this an a. Okay, so that's what we also denote this. So we also write add a is equal to x of x means bracket x with a. Okay. So that's the standard and adjoint representations. Okay, so very, very important. And let's just start kind of, let's go to line quickly. Next set of examples. Okay, so let's just start kind of going, let's start in dimension 1. Okay, so well, if the Lie algebra is of dimension 1, right? If I'm putting a bracket structure on it, so first of all, it has to be skew symmetric. So that means if I choose any element in X in bracket G, it brackets with itself to be 0. Okay, so the one-dimensional Lie algebra is not so interesting, but if I think about a representation, okay, then pi, okay, so let's take a representation of a one-dimensional Lie algebra. Okay, so this is a homomorphism from frac G into GLV. Okay, this is determined by any non-zero element in there, right, in the Lie algebra. Because this is, in particular, this pi is a linear map. So if I know what pi of x is, I know what pi of any scaling of x is, right? So pi of lambda x is lambda pi of x. Okay, but so understand what is this pi of x? It's just a linear transformation. So understanding this guy, okay, well, that's a study. That's what you do in linear algebra. Okay. So understanding what sort of how these guys look like and can they be represented in a nice way, that's what we study in linear algebra. Can it be diagonalized? Can you diagonalize this linear operator with a nice choice of basis on capital V? And a lot of times you can, but not always, right? You have Jordan forms. So tell me if I'm going to if I'm scrolling too fast, okay? So let me just remind you, so over C, so the Jordan forms classify the possibilities. Okay, so for example, so for T, let's take the matrix something like this. Okay, so you have these blocks. Okay, so you have a large Jordan block over there, small one over here. Okay, so with respect to the basis, E1, E2, E3, E4. Okay, so this is the first, second, third vectors. This vector. Okay, what are the invariant subspaces when you let this act on C4? C4. What are the invariant subspaces here? So the span of the first one is invariant subspace. Span of the third and fourth, these are invariant subspaces. Okay. So when I have invariant subspaces, this allows me, for instance, to decompose my my linear operator, right? I could look at the action on these invariant subspaces. Okay, so it's a divide and conquer type attitude towards just breaking up your study of this big and complicated thing into smaller pieces. Okay, so we're going to want to do this, but the first question to ask is, can you always do this? So given a representation, can one always decompose V into a direct sum of invariant subspace? Okay, that would be really nice if we can, right? Then we could carry out this divide and conquer approach. Okay, but unfortunately, it's not true. Okay, so the answer is no. And we'll do a quick example. Okay, but the good news is that the answer is yes for nice G and the corresponding V algebras. So what do I mean by nice? These are, so what I'm referring to here about, like, given a representation, can one always decompose into a direct sum of invariant subspaces? This is a so-called complete reducibility property. Okay, so we'll get to that in more detail later. Yeah, so we just put it. Whoa, that's not good. Complete reducibility. Oops. Okay, so we'll get to this later. So that when I say yes for nice G, so this is in particular, so semi-simple. Okay, so in particular, SL2, SU2, SL3, etc., do have this nice complete reducibility property for their representations. So because of that, then we're going to want to study these building blocks. Like once you decompose, okay, then let's get the smallest so-called irreducible representations, try to understand those, and then those will act as atoms for the general theory. Okay. So, okay, so let's see. So that's the part. So let's get to two-dimensional. So yeah. So even one-dimensional Lie algebras here, right? Really, the study of representations amounts to the study of linear algebra. Okay, so in studying higher dimensional Lie algebras, right? We're doing some advanced linear algebra here, but there's a lot of structure that we're going to take advantage of. Okay. Some more examples. Okay, so let's go to 2 dimensions. So recall, up to isomorphism, there exists precisely two-dimensional Lie algebras. Okay. And so let me write them in a basis. Okay, let me take a basis X and Y. So, or two of them, and they're distinguished by whether Lie algebra is abelian or non-abelian. Okay, the abelian case, we know that x with x is 0 and y with y is 0 because of skew symmetry. So we just need to specify the bracket xy. Okay, so in the abelian case, xy is 0. In the non-abelian case, this could be in general looking like this, right? The output is something in the Lie algebra, so it's in the span here, okay? So the span of x and y. So in general, it's going to be looking like this, but exercise show that you could choose, if it's presented to you abstractly like this, show that you could choose a basis so that you could normalize how this looks, and you can make it look like that. Okay. So again, you start out with alpha x plus beta y, assume it's non-zero. Now choose a basis so that it looks like this. Okay, so let me call this a star. This guy is not nilpotent, but it is solvable. Okay, so look up those definitions that you saw before on what solvable means and what nilpotent means. Okay, so let's take a look at this two-dimensional guy. Okay, so consider G star. And let's define a representation. Okay, so define a representation. Let's call it. Oh, okay, let's get the pies. Okay, so. Okay, so notice how it's presented to you right now is just, it's an abstract Lie algebra, right? These are x and y are not matrices. It's just, this is a basis for a vector space, and then I put a bracket on it. Okay, you check that it's yeah, it satisfies Jacobi, so this is a Lie algebra. Okay, but now let's define a representation as follows. So pi of x, okay, I want to give you a matrix. Okay, I'm going to define it like this. All right. So this is a linear map. So I just need to define it on the generators on a base, and then I there I could extend linearly, define it in the entire. So this is the definition. Pi of x, this matrix here. Pi of y is this matrix here. Okay, so the first thing you should check is that it is a homomorphism, and this amount to. Okay, so you verify that's x, y, right? Remember defining the condition for being homomorphism. So homomorphism means that's 5x, 5y equal to 5xy. Okay, so for all. Okay, so so in verifying this, yeah, that's verifying this this homomorphism condition. Okay, so but this map here, right? In defining it like this is an injection. Okay, so this is we can also say this is a faithful representation. Okay, it has no kernel. So this is a way of really representing this frac G as some matrices. Okay. Okay, so so you could ask, see with those definitions I put up before, some quantities like variant subspaces. So first of all, is this how do these guys act on a general vector in the vector space V, which is V2 in this case. Okay, so then let me see, X acting on V. Okay, so, well, this capital X acts on this V just by left multiplication. Well, we're just going to get A0. Okay. Y acting on V, we're going to get B0. Okay. Particularly, both of them are multiples of the first standard basis vector. Okay, so the only non-trivial G-invariant subspace is, the span of 1, 0. Okay, that's the only one, right? So remember the question that we asked before. So given a representation, can you split it as a bunch of, can you split the vector space as a bunch of invariant as a direct sum of invariant subspaces? But in this case, the only non-trivial invariant subspace is the span of the first basis vector. Okay, so in particular, this guy doesn't have an invariant complement. Okay, so there is no invariant. Okay, so this solvable two-dimensional I often get this representation amount gives first counterexample to this hope of this divide and conquer sort of thing. Okay. Okay, let's continue on this example and just illustrate the adjoint representation. Okay, so the adjoint representation. Okay, so I'm going to write this adjoint representation out with respect to the basis x and y that we were presented with originally. Okay, so this guy in this basis is expressed via. Okay, so remember what the bracket relation was. I just put it in the top corner here. X, y is y, x is 0, y is 0. Okay, so if we're going to write out the adjoint representation, okay, so we have to specify what is x getting mapped to and what is y getting mapped to. It's getting mapped to this add x map. Okay, that's a linear map on frac G. I'm going to express it as identify it with, so in this basis x, y, okay, so as a matrix. Okay. So this is in this basis. Okay, so how do you do this, right? Standard linear algebra stuff. Add x, the map, right? I apply it to the first basis vector. Well, that's just 0. That's the 0 vector that I decompose with respect to the basis x, y. Well, that's just 0 and 0. So in the first column, I put 2 zeros. On the second basis vector, okay, the bracket with x gives me y. I decompose y in this basis, and I get coefficients 0 and 1. So you put that in the second column. Similarly with this other guy. Okay. So on the first basis vector, so I'm bracketing y on the left with x. So that's going to give me, from this, it's going to give me minus y. So it's looking like that. And then I bracket the second basis vector y with y. And so I get 0 and 0 in a second. Questions before I move on? Okay, this is just describing the adjoint representation for this solvable Lie algebra, solvable non-abelian Lie algebra very concretely. Okay, so you want to be able to write down these actions, these representations in an efficient manner. Okay. All right, so that's the two-dimensional case. So let me mention just briefly about the three-dimensional. Okay, so I'm not going to go in a lot of detail about the classification. Unlike in two dimensions where there's just two possibilities, in three dimensions, there's a lot of possibilities. Okay, so this is known as the so-called Bianchi classification of three-dimensional Lie algebras. It's different over R than over C. Generally, things in Lie algebra theory, representation theory, are easier over C. Okay, so, but yeah, I'll put some of these details, let you work through some of that in the exercises. Okay, so hopefully get that out in a few days. Okay, so but I'll just mention it here, the classification of three-dimensional Lie algebras. So this is called the so-called Bianchi classification. Okay, let's see exercises. I'll let you work through some of those details and see how much some of these items in the list arise. Okay. But I want to focus on one very important three-dimensional Lie algebra. Okay, so again, I'll define it abstractly first. So define three-dimensional. I'll emphasize abstract. When I say abstract, it just means it's not presented as a bunch of matrices. Okay, so it's presented, as we were doing initially with that two-dimensional example, as a vector space, maybe with a chosen basis and bracket relations on amongst elements of that basis. Okay, so define a three-dimensional abstract Lie algebra G via a basis, which I'll denote by capital X, capital H, capital Y in this order. Okay. And what are the brackets? So the brackets are as follows. H on X is 2x. X with Y is H. And H with Y is minus 2y. Okay. So these bracket relations, memorize them, ingrain them, and carve them in your brain. Okay, so these bracket relations are extremely, extremely important. Okay. So this structure is called, well, yeah, this is the Lie algebra SL2. Okay, but probably SL2 when it was first presented to you was as 2x2 trace-free matrices. Okay. So of course that is one way of presenting it. That's one realization, one representation of this Lie algebra structure. We're going to talk about other representations of SL2. So there are other realizations of this structure. Okay, so when I say representations of SL2, I want you to think that this input Lie algebra G as something abstract. Okay, so generators, so this basis, and you have these bracket relations. Okay, so what are ways of representing these on vector spaces? Okay, the 2x2 realization, 2x2 matrix realization is one way, but we're going to classify all of the ways. Okay, So let's note here. Okay, so X, H, Y is called an SL2 triple. Okay. So memorize those bracket relations because they're going to come up all the time. Okay, what's really striking is how important this SL2 is. Actually, Serge Lang, he wrote a book that's like 500 pages, which is entitled SL2. Actually, SL2R in that case, but I think so. We'll largely be talking about SL2C, just because again, the representation theory in the complex case is nicer. Okay, but it's extremely important. It acts as a building block for more general semi-simple Lie algebras. Just you have all of these SL2s intermixed in there, and yeah, understanding how they mix and behave relative to one another is something that we're going to flush out later on in this course. Okay, how do we encode that? How do we use these use our knowledge of SL2 in that broader study? Okay, so this is called an SL2 triple. We refer to G as the Lie algebra SL2C. Okay, if I'm working over C, of course. Three-dimensional abstracts. Complex. You could also do it for the reals, of course. That's fine. Okay, so of course we have our standard representation. We have our adjunct representation. Okay, so the standard rep. Yes, this is pi from GL of C2. It associates to capital X, the matrix that looks like this. And to H, matrix that looks like that. Oops. This is not the only way of associating 2x2 matrices to Lie algebras. Okay, so be aware of that. Right? There's a lot of ambiguity, right? I mean, we've chosen a basis. If I were to take this realization right here, and then I take an invertible matrix, say capital A, I could conjugate each of these matrices. Okay, that would give me a new representation as 2x2 matrices with the same bracket relations. Okay, so yeah, there's ambiguity there, but like ambiguity in a controlled way, as in like you have a different representation, but it's isomorphic. Okay, you could choose bases to get these bracket relations, these same bracket relations. So isomorphic in the sense of intertwiners. So I'll review intertwiners later. Okay. Okay, but let's just stick with the naive way of representing things. Okay, so we have our standard representation. Okay, so right, the definition of representation says this lands in GL2C, but of course these guys over here are trace-free. So note that pi of G, right, is our usual trace-free matrices. Okay. But now, yeah, just referring back to what I said at the beginning about, okay, I have a representation. You could talk about invariant tensors on that, in this case, the vector space C2. So let me just make a remark, and then we'll get back to this later, that this vector space C2 is going to admit an invariant tensor. In particular, it's a G invariant so-called volume form. Okay, so I'll make that more precise later. Let's get to the adjoint representation. Okay, so here, the ad map takes something in G and gives you something in G at G. Okay, G is three-dimensional. So this, once I choose a basis over here, we're talking about GL3C on the target side. Okay, so in a similar way that what I was doing before, I'm going to represent each of these linear operators that I get for an input over here. I'm going to represent it with respect to a basis. Okay, so with respect to the basis, well, the SL2 triple basis, so X, H, Y, let's see what these matrices look like. Okay, well, the linear operators are, okay, add X, give me some matrix in this shows a basis. Okay, then I'm going to do H, oops, add H, that's a matrix. Then you have Y. That's matrix. Okay. So just let me just write down the answer and I will let you verify the details. Okay, so 0, 0, minus 2, 0, 0, 0, and then H is the nice one. It's nice and diagonal. Okay, so we're going to want to keep that in mind. We like diagonal or diagonalizable linear operators from linear algebra, and that's very much going to be part of the game as we go along. Okay. Oh, sorry. Okay. Again, there are nice invariant tensors. Okay, so on the representation space, in this case, G, okay, this admits a G invariant non-degenerate symmetric bilinear form. Okay, so it's like a metric in the real case, except here we're working over C. But be careful, it's not a Hermitian metric I'm talking about, because Hermitian is it's conjugate linear in one of the slots. Okay, here it is bilinear. Okay, so C linear in each entry. So we have a G invariant bilinear form, and so you've seen earlier on in the course that when you have a bilinear form, then that defines the so-called orthogonal group, special orthogonal group that preserve linear transformations that preserve that bilinear form. Okay, the Lie algebra there is so-called SO3. So add, apply to all of these guys. This is, well, by default, it's sitting inside GLG, but because I have a symmetric bilinear form, it's actually something smaller than, it sits in something smaller than GLG or GL3. It's sitting inside SO3. Okay. So B itself is dimensional. Map sends it something. Well, it's sitting in something three-dimensional here. You can show that there's no kernel. So in fact, this is going to be an isomorphism. Function B 3. Should also say and is faithful then this add map is actually specifying an isomorphism between SL2C and SO3C. So what we're going to get to, not today, but I mean there is like what is it? What exactly does this mean? Okay, and for other representations, what sort of other invariant tensors arise? Okay, so this symmetric bilinear form in this adjoint representation case is one instance of a larger picture. Okay, so I think actually we are at 1 o'clock, so maybe let's take a break and then we'll resume at quarter after. Okay, I'm going to stop the recording. Okay, so let's continue. Let me put up an exercise. Just we're getting a feel for these representations, right? So, oops. Okay, so exercise. So one thing why all these different kinds of vector spaces were introduced, like tensor product vector spaces and dual vector space, direct sum vector spaces. This is a way of building up more general representations from ones you know about. Okay. So it's good to recognize when you have a representation that comes from something simpler, right? So this is this exercise is about supporting that. So from the standard GL2R rep or GL2C, doesn't matter, we get an induced GL2R representation I on so-called symmetric two tensors. Okay, so the space of well, the standard representation is just R2. Symmetric two tensors looks like this. Okay, so I'm going to take V squared for any vector in R2, and then I'm going to consider it squared, as in this is V tensor V, but often we'll just use this shorthand, V squared. Okay, but I'm not just going to take the collection of these guys, I'm going to take their span. Okay, I'll make this very concrete shortly. Okay, so but how do we induce a representation? Okay, so I know how to act on R2. I want to act on S2 of R2. Okay, so I need to tell you what is pi of A. Okay, so pi of A is an element of GL of this vector space. Okay, so well, it's defined to let it act on some spanning vectors, right? So on a basis, say, but or here generators are described by V squared. So I just need to specify how this acts on V squared. Okay, and then so how I'm going to let that act is let A act on V, and then take its square. Okay, and this is actually well defined. Okay, and well, since this vector space is the span of such, I do have to extend whatever definition I have here. I need to extend it linearly to the entire vector space. Okay. So I haven't got to the exercise part. So okay, so let's make this more explicit. Okay, so let's take a basis of R2. Okay, so it'll be the standard basis of R2. Okay, exercise part. Show that this representation, okay, so let's just get the input and output correct. So it's a representation of this group GL2R on the vector space S2R2. So it has target in GL2, GL of S2R2. So this is expressed as the following. Okay, so I'll think about elements of GL2 as usual as invertible matrices, A, B, C, D components, okay, with AD minus BC being non-zero. Okay. But now S2 of R2, okay, so the first question is, what's the size, what's the dimension of this vector space? And it's in fact going to be three-dimensional. Okay, so I'm going to choose a basis. Okay, so I'll let you think about that, but well, here's the basis. With respect to the basis, x squared, xy, y squared. Okay, so pi of this capital A right here, I have to describe a 3 by 3 matrix. Okay, and so here are the components. A squared, 2ac, c squared in the first column, ab, bc plus ad, cd, and then last column. Okay, so this is an over here is an element of this guy over here. Okay, so just run through the computation of inducing this representation from the standard representation. Okay.
I have a question.
Yep.
So you have the basis here for S2R2.
Yep.
With the product of X and with Y.
Yeah, so usually I guess you call it E1 and E2, but I'm going to call it X and Y here.
Yeah, so this is a tensor product of X and Y, right?
Here, yeah, it's a tensor product of X and Y.
Yeah.
So I can't remember how Erland defined it, but I would define it like that. Stay with the how.
Oh, okay. Yes, thank
That's
you.
what
Yeah,
X,
it's
Y
a symmetric tensor product.
It's a symmetric tensor
Yeah,
product.
yeah. Yes, great.
Yep.
Thank you.
Great, thank you. Any other questions? Okay, I'm going to scroll up to here. Is that okay? Okay. Let me just remind you about this transition going from the group to the Lie algebra. Ooh, sorry. Okay, so given G representation, capital pi V, you always can get from it a frac G representation. Okay, so for the Lie algebra. And this is coming from this, how it acts on exponentials. Okay, so pi of the exponential ex is e pi x. So for all x and g. Okay. Okay, so hopefully you saw that before. Okay, so let me just recall a couple of properties. Okay, so it's pi of x, right? You obtain that by differentiating at the identity the curve in the group determined by these exponentials. Okay, so e to the tx, right? This is a curve in the group that passes through the origin at time t is equal to 0. I apply pi to this, so this is now a curve in GL of capital GL of v, and then I want to differentiate that. So this is going to get into little GL of v. It's an endomorphism. Okay. Okay, that's property number 1, and property number 2 how does it behave with respect to this conjugation by an element of big G? So there's this nice conjugation property over here. Okay, so okay, so any representation of the group, big group, it doesn't have to be connected, or but yeah, there's a you can nicely associate a little g representation. Okay. And you could ask the question about going the other direction. Does every little g representation come from a big G representation? Okay. Question. So does every G representation come from a big G representation? And the answer is no. So the smallest example of this, or a nice example of it, is the so-called spin representation. So this two-dimensional complex representation, it is an SO3 rep, and that's not too hard to see because something that you've seen before, SO3 is isomorphic to SU2. So as a Lie algebra, okay? And so I'll recall the definition of SU2 shortly, but little SU2 is a bunch of complex 2x2 matrices, okay? Skew Hermitian, trace-free. So because the standard realization of SU2 is as 2x2 complex matrices, of course that acts on C2. That's but it's not it is not a big SO3. Okay. One thing you do get is but if you have some nice topological conditions, so in particular, if G is simply connected, let's be safe and just say it is connected, simply connected. Then everything's okay. Okay, so then if you have a Lie algebra representation, there will be a representation of the corresponding Lie group, simply connected Lie group. Okay. So recall, so I think he showed you guys the Dirac-Beltrick business. Okay, so the fundamental group of SO3 is Z2. Okay, that's not simply while SU2 is any questions for I'll focus on SU2 in a more detail. Just use examples, nice class of examples of these representations of SU2. Okay, in particular, irreducible representations. Okay, so examples of irreps of big SU2, little SU2, and its complexification. Okay, so let's first recall SU2. So capital SU2 consists of those matrices complex such that if I take conjugate transpose times A itself, then you get the identity. Okay, so these are unitary matrices, but you also want to add this determinant one condition. So that's the S part. Okay. You can make this explicit. Okay, so these are matrices that look like this, so complex, alpha and beta complex. And then the one condition tells you that the sum of the norm squared of both of these guys is 1. Okay, so SU2 topologically, because of this condition, right? SU2 is homeomorphic to the 3-sphere. Okay, and the 3-sphere we know is simply connected simply connected. At the Lie algebra level, we've also seen that matrices, this consists SU2, little SU2, consists of 2 by 2 matrices. That's okay. So this product here, when you take the Lie algebra, right? I take a curve, so A as a function of t. Okay, A is so A star, A of t star times A of t is equal to I. Okay, and I want to differentiate that curve at the identity. So because I have a product here, I'm going to have to use product rule. Okay, and then I evaluate everything at the identity. So this product will translate into a sum, okay, at the infinitesimal level. And so SU2 consists of those guys that are skew Hermitian and trace free. Okay, determinant one converts the infinitesimal law to this trace free condition. Again, I'll make that explicit. So these are matrices 2 by 2. They'll look like this. Here, A, B, and C are all real. Okay, so that's big SU2 and little SU2. Okay, so let's talk about representations of both of these guys. Here, is that okay? Okay, so let's define a vector space. The degree M homogeneous polynomials defined on C2. Just for later reference, okay, this VM is the same thing as symmetric nth power of C2 dual. Okay, so if you're not used to dual spaces yet, this might be a little bit awkward, but yeah, we'll try to make it a bit more concrete later on. Okay, so but right now let's just think about this as polynomials. So any guy over here, it's a function, right? It's a function. Keep that in mind, it's a function, as opposed to sometimes I'll talk about polynomial symbols at some later on. Here, it's a function that takes as input some z, and that z has 2 components with respect to the standard basis in C2. And then the output is going to be an nth degree polynomial. Okay, so something that looks like this, where these constants are all in C. Okay, so we have these functions. Okay, so I need to give you an action of SU2 and little SU2. It's going to take as input a function and spit out a function. Okay, so we're going to define the complex representations. Okay. So big pi m. So what is this going to do? So given a U, a unitary matrix here, I'm going to assign to it. Okay, so given an F in VM, I have to tell you what this symbol means, U dot F, right? It's going to be another polynomial. So what is this polynomial? A polynomial is going to be defined, well, it's defined by what it does to some input, Z, right? So I have to define what that means. So what does this mean? Okay. By definition, what I'm going to do, okay, so first of all, this U dot, right, is just shorthand notation for this, putting this, all this pi stuff. Okay, so what does this mean? Okay, so this is, I take the input Z, and I'm going to put a U inverse. Okay. So does this make sense? Well, U is a unitary matrix. It's a 2 by 2 unitary matrix. So, well, it's portable, right? I could make sense of what U inverse is. This is a 2 complex matrix, and I let it act as something in C2. Okay, so this is something in C2. Then I fit it into the F that I'm doing. Okay. Plus, this definition reasonable. Okay. Any questions on that? So I'm letting this, I'm doing this inverse because otherwise, if I didn't, I'm not going to have the axiom for group homomorphism being satisfied. It would be an anti-homomorphism. Okay. So when talking about group actions, I'm also talking about a left action. If I didn't put this there, it would be a right action. Okay. So I need that to make everything consistent. Similarly, let's go to the infinitesimal level. Okay, so here is let's call it an S, and then okay. So what does this mean? It's getting horrible. So S dot F. Okay, so little im. Okay, so I have to define what this means. So you pass from the group level to the Lie algebra level through a differentiation. Okay, so what are you supposed to do? You're supposed to take so associated to this S, I take the corresponding exponential, e to the TS. So that's my U. And then I invert it, right? That's what this is telling me to do. So I invert it, and then I apply it to Z, feed it into this F, then you differentiate. Okay. Okay, so let's make this concrete in an example. Okay, so let's let U be diagonal into the T. Oh, why am I putting it? So let's take this matrix here. This guy is in SU2. Okay, it's so if you take U star times U, it's the identity, and it's also determinant 1. And let's take an element in V4, so M is equal to 4 here, with when you feed in Z, let's look at Z1 cubed Z2. Then. Okay, so let's let this act. U on F Okay. So this is a new function. So we have to, I want to identify which function that is. So we have to let it act on a z. And by definition, this is u inverse of z. Okay. More explicitly on z1 and z2. So this is going to be right. I take the inverse of u and apply it. Yeah. F, my chosen F that I'm acting on is this guy. Okay, so I feed all of this into my F. And it says, well, take the first component, cube it, and then multiply it with the second component. So I have e to the minus it, z1, all cubed, times the second. Okay, so so I take that exponential, I get minus 3 of them over here. And then one of them over there. So e to the minus 2it times, oh, things are going crazy, go away. Let's see, e to the minus 2. Okay, but this is just what I started with, right? So this is e to the minus 2it times. What I just shown is that, so that's what happens for each z. So u acting on the function f is e minus 2t. Okay, so that's the output of this calculation. When I differentiate this guy at t is equal to 0, and then yeah, so do the evaluation at t is equal to 0, I'm going to get the corresponding infinitesimal generator. Okay, so this is an element of little su2. And we have capital U is e to the t s. And okay, so the infinitesimal action, okay, well, this is take the derivative at t is equal to 0 of, okay, so I'm doing that, right? Right, but this guy is e to minus 2i t f, right? So I'm getting minus 2i times f. Okay. So this s is acting by a simple multiplication by minus 2i here. Okay. So that's this one example, okay, of how do you use this definition of the representation in this context. Okay. So compute sometimes in yeah, if I have something at the Lie algebra level, I don't always want to go to exponentiate to the group level, let it act at the group level, and then infinitesimalize afterwards. Okay, I want something more direct. Okay, so let's get a more general formula. Okay, so if I have this Lie algebra element and this polynomial, so we can calculate S on F efficiently by the following form. Okay, so I'm going to take S on F instead. Okay, definition says I should exponentiate and then take the inverse and then apply it to Z, and then feed that into F, then differentiate. Okay, so what we can do when we do this differentiation is just use some chain rule. Okay, so this says I should go take a derivative with respect to the first slot of F, and then I differentiate what's in the second slot. Okay, so I'll write that as, okay, so this is what's in this, sorry, the second slot, the J slot. Okay, so this is just their chain rule. Okay, and I want to evaluate everything. Oh, my biggest. T is equal to. Okay, so let's just be clear about what I've written here. So this is a vector in C2. I could talk about its either the first component or the second component. So that's what I put in the subscript over here, the jth component. Okay. So yeah. So this is a straight out chain rule thing. And so I could evaluate this derivative here as follows. Okay, so I have let's just rewrite it. Okay, so I have minus S Z jth component. Okay, so when I take this derivative, I would normally get minus S coming out front multiplied by an exponential, but then I'm doing this evaluation at t is equal to 0. Okay, so that's why I only have this minus S coming out here. Okay. Okay, so so I have this summation, and then I can just write it out really explicitly. So SJK. J is the row index, K is the column index. Okay, so I get this direct formula that's, yeah. So from this, I use this formula to get what the action is on this input F, okay, given one of these S's. Okay, so in applying this directly, you don't have to go through the group anymore, right? It's using this chain rule. And yeah, you get an efficient formula. Okay, so so we could use this formula for other generators in SU2. Okay, so in this way, you get we started out with the group action. We could get to the algebra action. Okay, now let me pass to the complexification, okay, of the Lie algebra, and define its action. And the reason for doing this is really just in working in the complexification, linear algebra is a bit nicer. Okay, there are nicer bases adapted to what's happening in the complex world. Okay, and we know that we can always do this because, yeah, given any representation of a real Lie algebra, okay, taking values in GL of a complex vector space, there's a unique extension to a representation of the complexified object. Okay, so this is something that I think you guys talked about already with complexification, but let me just state this all. Okay, so we can extend this guy uniquely to a representation of the complexification. Okay, which is SO2C. Okay, and I mean, the idea here is that, okay, so the complexification consists of vectors that look like that, where X and Y are in SU2. So if I know what pi of X is and pi of Y, so I want to define what pi of X plus IY is, right? Well, but this is just, if you want it to be complex linear, it should be like that. But I know what this is, and I know what this is. Okay, so therefore, you have a representation of the complexified Lie algebra. Okay. So okay, so via this star over here. So via the formula here that can be fill out. Oh, sorry. We're talking about SL2. We have so spanned S2 is spanned by this guy. This guy. Yeah. Okay, our SL2 triple. Okay, so these are the specific S's that we're going to be looking at. Okay, so these guys are existing in this complexification. Okay, we're going to let that act via this formula. Okay, to get the following ways of realizing the action. Okay, so check this. Okay, it's an exercise to check this. So via star, okay, we get the following. So IM of X is minus Z2 partial Z1. IM of H is minus Z1 partial Z1 plus Z2 partial Z2. And lastly, what does it ask? What's the Y action? Okay. So, so go through this computation, okay, on your own, okay, but it's really just a direct application. Okay. So we have these generators here. So let's do an example. Okay, let's example today. So examine the M is equal to 4 case. Okay, so note that, okay, if I'm going to let this X act on, say, the first guy, right? Homogeneous polynomials of degree 4 in Z1 and Z2. So how is this going to act? I use this guy. Okay, so I just apply it directly to this. So what I'm going to get is minus, 4 Z1 cubed Z2. Okay, so I'm just directly applying this differential operator to this function. So similarly, X on this guy, so that's going to give you minus 3 Z1 squared, so 2 squared, okay, etc., etc. Okay, so you can run through all these computations, but I want you to have this bigger picture and more kind of this abstract picture of what's going to happen and how we're going to start thinking about these representations of SL2. Okay, so I want you to have this picture. Okay, so you have Z1 to the 4th over here. I'm putting brackets around there because I want to talk about the span. Okay, Z1 cubed, Z2. I'm not going to worry about these kind of constants up front for the moment. Okay. Okay, so X, what is it doing to this first Z1 to the power 4? It moved it over here, this next subspace. So we have X. X is also called raised operator. Okay, so moving from subspaces, why is it raising? I'll get to the once you get to the end, this is to the 4. If you hit it with X again, it's just to kill it. It's going to go to 0. Y, also called the pouring operator, moving in the other direction. So where does raising and lowering from? Each of these subspaces, I could ask, how does H act? Remember, H was this nice diagonal guy. At least in the standard basis. Okay, so each of these subspaces here are in fact eigenspaces for H. So what is the eigenvalue? It's -4 over here, -2, 0, 2, and 4. Okay, so X here, it's raising the H eigenvalue, while Y, the lowering operator, is lowering the H eigenvalue. Okay. So, any questions before I move on? Okay, so I mean, this is just a schematic of what's happening, but it's something that you should really keep in mind, because for general SL2 representations, it's a similar game. Okay, but as far as the theme today about kind of making representations concrete and thinking about matrices, so let's do that. Okay, so with respect to the H eigenbasis that we have, I'll just say above. So this X, or rather pi, pi4 of X. So it's 5-dimensional space, okay? So I have a 5 by 5 matrix. We have this nice strictly low triangular structure for this X. For H, okay, so it's -4 diagonal in the position. And then my okay, great. So here it's strict triangle. Okay. And you could check, well, I mean, this is a representation, right? So this is another way of so a 2x2 realization for SL2, 3x3 realization for SL2, the adjoint representation, and this is a 5-dimensional realization. Okay, you can check with these matrices that, yeah, if you check those bracket relations that we had for SL2, that they are satisfying those bracket relations. Okay, this is another realization. Okay. So I think we are at time. So are there any questions before I close this first lecture? Okay, so if not, I'll turn off the recording.